Week we studied motion in one dimension. Our final goal was really studying motion in three dimensions. Okay, and the reason we started off studying motion in one dimension was the projection of this three-dimensional motion along each axis was independent of each other. And that's what that statement means is when you try and change the motion along the x-axis, you don't affect the motion along the y and z axis. When you give an acceleration along the x-axis, the velocities do not change along the y and z axis. Okay, so that's why we could treat the motions in each dimension independently. Okay, so we'll talk about motion in three dimensions. Okay, so here's an example. Here's a okay, this is all right. Well, it shows you in two dimensions, but it doesn't matter. Okay, here's an object moving in a general trajectory. Okay, and you saw that the description of this motion, here we go. So here's a object and it's moving. Here's its general trajectory. Okay, now if you want to describe this motion, we learned that describing this motion involved giving these three functions: x as a function of position, y as a function of position, and z as a function of position. Okay, if you give me these three functions, you've completely described the motion. Okay? And from this, you can calculate all the things that you're interested in calculating about the motion. Okay? So for instance, you wanted to calculate the velocity at any given time. You saw that the velocity at any given time was the time rate of change of the position. Yeah. And here's another thing you're interested in. What is the acceleration at any given time, which is equal to the time rate of change of velocity. Which is the second time derivative of the position. Okay. And generally, those are the things that you're interested in. Okay. So, again, this is a complete description of the motion. Okay. And once you have this description, you can calculate the velocity. Okay. This would be the x component of the velocity. This would be the y component of the velocity. This would be the z component of the velocity. Okay. Here's the acceleration. Okay. Acceleration. This would be the x component of the acceleration, y component of the acceleration, and z component of the acceleration. Okay. All right. Last time we briefly mentioned this, but here is a okay. So let's say you want here. I'll write down an equation for a motion. Okay. So here's a spiral motion. Yep. The equation of this motion is, okay, the description of this motion is, so let's say 5 cosine omega ti plus 5 sine omega tj plus okay, so this equation describes a spiral motion. Okay. Starting on the x-axis, the radius of the circle is 5, and the velocity along the z-axis is 7 meters a second. Okay, so that's that motion. Again, you can describe any motion by giving these three functions. Okay. And so if you had this motion, let's calculate the velocity at any given time. You'll be interested in that. The velocity at any point turns out to be tangent to that curve. Okay? Yep.
So what's the cosine WT?
It's omega t.
Okay.
Okay? That's the angular velocity. All right, so let's say, so here, and again, like I said, the velocity is tangent to the curve, and in this case, the acceleration is perpendicular to the curve. Okay. Okay. So let's calculate those things. So this is a fairly simple example. RT, you saw what the motion was, 5 cosine. Okay. Vt is the time derivative of that. Derivative of cosine is negative sine. So So there's the constant velocity along the z-axis, okay? And there's the x and y component of the velocity, okay? And you can see that as you are traveling along a tangent, there's the velocity, and this velocity's x and y component are changing, which is what this equation is telling you, okay? And then the other thing you're interested in is the acceleration. And this is again minus 5 omega squared cosine omega t I minus so the acceleration is in the xy plane, okay? And the acceleration vector, see, it has no z component, and it'll be always pointing toward the center of the circle. Okay. All right, so that's what we are interested in this chapter. Yep. Do you guys understand? All right, so we are interested in describing 3D motion. And when we ask you for a description of a 3D motion, we are asking you for these three functions, and we'll be interested in calculating velocity and acceleration, and you know how to do that. Okay? Yep. In that example, yeah. Okay. So here's a spiral. So there is something called an osculating circle. Okay. So at any point on the curve, you draw a circle that's tangent to the curve, and the plane of the circle is oscillating, and that's in the xy plane. Okay. All right. Anyway, so what is it that so when we are asking for a motion, we are asking for these three functions. And once you have the position as a function of time, you can calculate the velocity and the acceleration. Yep. Do we understand that? All right. So now I'll quickly go over the slides. So this is motion in 3 dimensions, and then we'll consider a special case. We'll consider a motion in 2 dimensions. And the reason we are interested in that is when you throw an object, and when it's traveling only under the influence of gravity, it is traveling in 2 dimensions. That motion is in 2 dimensions. Okay? And we throw things around quite a bit, so we will talk about that special case. Okay? All right. Here's an interesting picture. Okay, so if you get on a tall tower and throw a tennis ball or whatever, and if there was no air resistance, and this is the center of Earth, what is this trajectory? I'm sorry? No. This trajectory is, okay, what it does is if it could go through Earth, it would be an elliptical trajectory with the center of the Earth as being at one of the focus. Okay? And this is exactly like the trajectory of planets with the sun at one of the focal points. Okay? And as you throw it with greater and greater velocity, the eccentricity decreases. And if you throw it at 8 kilometers a second, again, this is ignoring air resistance and stuff like that. And you can do that if you go up 200 miles, if this tower was 200 miles up. Okay. Then you would go around the Earth in a circular orbit. And that's what the International Space Station does. Okay. All right, so we will describe 3D motion. Okay. So let's say this is your motion. Okay. So your position at any given time is given by this position vector with reference to this coordinate system. Okay. Now, the coordinate system you choose is just the language you're describing. So here is, let's say, x prime, y prime, z prime. Then your position in that coordinate system would be r prime, t. Okay? So your position is with reference to a coordinate system. So the same motion described in different languages okay. You'll get different functions, but it's describing the same motion. Okay. All right, so here's a description of the motion. You want the velocity at any time, you just take the time derivative of this vector. So here's the x component of the velocity, here's the y component of the velocity, here's the z component of the velocity. You want the acceleration. Acceleration is time derivative of velocity, okay, which is the second time derivative of the position. So here's the x component of the acceleration, y component of the acceleration, and z component of the acceleration. Okay. All right, any questions? I'm going, like I said, you already saw the entire chapter in 5 minutes at the beginning of the lecture. Okay. Now we'll just go through some terms. Okay, so if this is your trajectory, the displacement, that's your location at time 1, and this is your location at time 2, there's your displacement vector. Okay. And the displacement vector is your position vector at time 2 minus position vector at time 1, or your position vector at final time. So, okay, so this is maybe more intuitive. Final time minus initial time. And this is easy to see because the final position vector is the initial position vector plus delta r. Okay, there is your initial position vector plus the displacement is equal to the final position vector. Okay? So your displacement vector is the final position vector minus the initial position vector. And it's a vector pointing from your initial position to the final position. Okay. Your average velocity between these two instants of time is pointing in the displacement along the displacement vector. Okay? The average velocity is displacement vector divided by the time over which that displacement happened. And this is a vector divided by a scalar. And so dividing by a scalar just changes the magnitude of the vector. So the velocity is pointing in that direction. But of course, we are interested in instantaneous velocity. Instantaneous velocity is limit delta t going to 0 and this is what we call dr by dt. Again, that's the instantaneous velocity. And as we mentioned, the instantaneous velocity is always, so at this instant, the instantaneous velocity is pointing in this direction. At this instant, the instantaneous velocity is pointing in this direction. The instantaneous velocity is tangent to the curve. Okay. What is the magnitude of the instantaneous velocity? That's how fast you're going at that point. So you could be going in a circle. Okay. On a circular road, one person is traveling faster than the other, and their magnitude is greater. The direction is the same. Yep.
I was just wondering if you could go back to the formula for instantaneous velocity. Thank you.
Mm-hmm. So instantaneous velocity is what we're interested in. It's dr by dt. Okay. So for instance, going back to this, if you wanted the instantaneous velocity at this instant, okay, there's the vector, and the magnitude and direction of this vector is contained in, all that information is contained here in that function r. Okay, so it's contained in the derivative of r. Okay. All right, so there's the x component of the velocity, y component of the velocity, z component of the velocity. So here's, for instance, if you go to this page, the Wikipedia page, there's a, yeah, so here's a nice three-dimensional motion. Okay, so you see the brown vector is the velocity vector, and the green vector is the acceleration vector. Yep. When do you accelerate? When your velocity changes, you're accelerating. Okay? So average acceleration is defined as change in velocity divided by change in time. Okay? So for instance, for this trajectory, there was the initial final velocity, there's the initial velocity, and so initial velocity plus change in velocity is the final velocity. There was the change in velocity. There's that guy. Okay? So between those two instants, the acceleration is pointing in this direction. The velocity is changing in that direction. Okay? So acceleration is change in velocity divided by the time over which that change happened. Okay, if the velocity does not change, if this is 0, acceleration is 0. Okay. All right, here's what you want to notice about acceleration. Velocity is always tangent to the trajectory. Okay. So let me give you a physical intuition. So let's say this is a curved road you're driving over. Okay. Now, if your speed is constant, then you will not have a tangential acceleration will be 0. Okay. But see, if speed is constant, okay, so this tangential acceleration will be 0. But well, okay, let me change that. Tangential acceleration will be 0. Okay. So here's the velocity. Is the velocity changing on this curved road?
It'll change its direction.
There you go. So the velocity is changing. So the centripetal acceleration is not 0. Okay. So when you're going on a curved road, if you're going at constant speed, if you hit a curvature, then your velocity is changing and you're accelerating. And which way is the acceleration pointing? It's pointing. What you do is you complete a circle, and the acceleration is pointing towards the center of the circle. Okay. Now, what happens if your speed is also changing? Well, you will certainly have this acceleration, but you will have tangential acceleration as well. Okay. So tangential acceleration is due to this change in speed, and the centripetal acceleration is due to the change in direction. Okay. So you have to contend with two kinds of accelerations, okay, when you are on a curved trajectory. So tangential acceleration is change in speed, and centripetal acceleration is direction, and change in direction of the velocity vector. Okay. You sort of already knew this, but it was so for instance, when we were doing one-dimensional motion, the only thing that really changed was the magnitude of the velocity, okay, and the acceleration was tangent to the trajectory. Okay. So you had seen that already. Okay. The acceleration, whenever the acceleration was due to this change in speed of the object, the acceleration was tangent to the trajectory. And then you saw the other extreme example. You saw the velocity changing without the speed changing, and the acceleration was perpendicular to the trajectory. So we had already introduced this to you guys, except in special circumstances. Okay. All right. So in this diagram, there is your trajectory, and there is the total acceleration. So this motion has a tangential acceleration and a centripetal acceleration. Okay. This diagram. Okay. So the tangential acceleration is tangent to the path, and the centripetal acceleration would be centered to the path. They've just done the component of the total acceleration in terms of along these axes, x and y component. Okay. So for this trajectory, since there's the total acceleration, you know that the speed is changing as well as the direction is changing. Okay? So this has both tangential and centripetal acceleration. Okay. So again, acceleration is dv by dt. Okay, so that's what you want to remember. So there is the x component of the acceleration, y component of the acceleration, z component of the acceleration. All right, so what we have said is, okay, so here is a three-dimensional description, a motion occurring in three dimension. Here is a description of the motion. What you're interested in is the velocity, which is dr by dt, and acceleration, d square r by dt square. Okay, that's all we've said so far. Now, what we're going to do is we're going to consider a special motion, a motion under the influence of gravity alone. And this motion occurs in two dimensions. Okay. And so we'll consider motion where we only have to give, we only need x and y coordinates, okay, or any two coordinates, y and z or x and z, whatever you want to call them. Okay. All right, so again, given this, you could calculate that. Okay. So that's what we've done so far. Now we'll do projectile motion. So this special two-dimensional, we'll consider this special two-dimensional motion. In 2D, motion is under the influence of gravity alone. So what does that mean? That the only force acting on the object is the gravitational force. So there's no air drag, no lift. So we're not considering motions of planes or gliders and stuff like that. We're considering motions of rocks thrown in the air, or baseballs thrown in the air. Okay? So this is the motion we're considering. This is a free fall motion. Is this free fall? I'm sorry?
It would be free fall, but it's got wind resistance.
Yes, so there are lift forces and drag forces. And those other forces are comparable to this gravitational force. Okay? So in this case, the drag force was negligible. There was drag force, but it was negligible compared to gravitational force. Okay? So that's what we're considering. Okay, so air resistance is negligible, and so on. And what we're going to show you is that, so if you throw an object and it travels only under the influence of gravity, this trajectory is a parabola. Okay. And here's a couple of things you want to notice. Okay, so if you throw this object, all right, so it's only traveling under the influence of gravity, so the acceleration due to gravity is a vector in this direction. Okay, and so in this coordinate system, see, this acceleration has no x component, it only has a y component. Okay, so this acceleration is 0I minus gj. Okay. All right, so here's an equation that you saw before last time. What does this say? This tells you the final velocity. The x component of the final velocity is the initial x component of the velocity plus x component of the acceleration times time. Well, for this guy, what is the x component of the acceleration? It's 0. This fellow is 0. So you see, the x component of the velocity does not change. Okay, so when you throw a ball up, that's what you can see. See, the x component of the velocity remains constant. Okay. Well, whereas the y component of the velocity changes. So as time increases, the y component of the velocity is changing by that amount. Okay, so when you throw a projectile up, the y component of the velocity is changing. Okay, whereas the x component of the velocity remains constant. Okay, all right. The horizontal and vertical motions are independent of each other. The trajectory of a projectile is a parabola. Okay, so here is an interesting example. All right, so I'll drop this and we'll time it. Let's say 1 second, keep it down. Okay. How long did that take to do? How long did that take? So this one took 1 second. Huh? So the y component of the motion is independent of the x component of the motion. For both these guys, the initial y component of the velocity was 0. So they took the same amount of time. All right. Now, if you want it to take less time, you'd have to throw it with the velocity like that. Okay, so that's what we mean by the horizontal and vertical component of the velocities are independent of each other. All right, well, that was an illustration of that. Okay, so the trajectory of, now what we're going to show you is the trajectory of this is a parabola. Yeah. And you guys remember from your calculus classes that the graph of a quadratic is a parabola. Okay, so essentially what we're going to show you is that when you throw an object under the influence of which is traveling under the influence of gravity alone, that the x and y coordinate of this guy are related like that. That's what we're going to show you. Okay. All right, so the x coordinate, so you saw that x minus x naught is v naught x t plus 1/2 ax t squared. Okay, so for this trajectory, the acceleration was 0I minus gj. Okay, so we'll say you start off at x naught equal to 0. X component of the acceleration is 0. The x position as a function of time is v naught x, which is the x component of the initial velocity, so v naught cosine theta. So there is the x coordinate as a function of time. Okay, so there is the x coordinate as a function of time, and you see it's linearly increasing with time. Similarly, let's write down the y coordinate. So y minus y naught equal to v naught yt plus 1/2 ayt squared. We'll say this is 0. Yt, the location is v naught sine theta naught t minus 1/2 gt squared. Okay, so what we're going to do is solve for t here and plug that in there. Okay. We solve for t and plug that in there in terms of, so t is x over v naught cosine theta naught. And we'll plug that in there, and this is what you get. And you see y is a quadratic function of x. And so that trajectory is a parabola. The negative, when a is negative, the parabola points downward. Okay? And that's what this is. All right, so we have shown that this is a parabola. Yeah. Now, it turns out that this is not exactly a parabola. It's a parabola if the acceleration is constant like this. But see, where is the acceleration pointing in this direction? Here, in this room. Huh? Yeah. Okay, so it's actually pointing to the center of the Earth. Where's the acceleration pointing here? It's pointing to the center of the Earth. Okay. So it's not really vertical to the ground, but for small distances, it's we'll say it's constant and it's perpendicular to the ground, and then it's a parabola. Okay? Now, if you throw this, so if you throw this baseball and it reaches New York, if you can throw the ball that far, then it would not be a parabolic trajectory. Okay? It would be part of an ellipse. But we're not throwing baseballs to New York, so parabola is good. Okay?
So over smaller distances, it's just negligible.
Right. So as long as the curvature of the Earth doesn't come into play, if you don't throw it that far, then you're good. Okay. All right. So the trajectory is parabolic under what circumstances? Under if the gravitational acceleration is constant, so you're not throwing it very high, the magnitude of the acceleration is not changing, air resistance is negligible, and so on. Okay, so for our purposes, it's a parabolic trajectory. Okay, so this is called the range. The horizontal distance the object travels when it's come to the same vertical location. Okay. And the range is given by speed square, initial speed square times sine 2 theta naught, okay, divided by g. Okay. Now for a given speed, you see as you change the angle, the range will change. But the maximum value this function can have is 1, and that happens at 90 degrees, so theta naught is 45 degrees, and you all know that. So you get maximum range with an initial launch, with a launch angle of 45 degrees. The maximum height this projectile travels is v naught square sine square theta naught divided by 2g. And of course, for a given speed, the maximum height is achieved if theta naught is 90 degrees, if you throw it straight up. And you can see that in this formula. For theta naught equal to 90 degrees, you'll get 1 and you get maximum height. Okay. All right, all the information is contained in the equations. Okay, so that's what you want to learn to do. You want to start reading the equations. Yep. Here's another deal. It turns out that for complementary angles, you get the same range. For 75 degrees and 15 degrees, you get the same range. Okay, so 60 and 30 degrees, you get the same range. And so what that means is, so if you go back to that formula, what that must mean is, okay, so here's the range formula. So what that must mean is sine 2 theta should equal sine 290 minus theta. Okay, sine 2 theta should equal sine 180 minus 2 theta. And well, you know that sine theta is equal to, so treat that as phi. Sine phi is sine 180 minus phi. Okay. So sine phi and sine 180 minus phi give you the same value of the sine. Okay. So this fact is a reflection of that. So when is the trajectory parabolic?
Constant.
I'm sorry?
You have a constant velocity.
So when the only force acting on you is the force of gravity. Okay?
Is that
That-
constant velocity or constant acceleration?
Acceleration is constant. Okay. Well, so, but if you have a force of gravity and you have a constant drag in that direction, your trajectory won't be parabolic. Yep. So, of course, in real life, there's plenty of drag present. Okay, so here are real baseball trajectories. Okay, so this would be the parabolic trajectory, but there's the real trajectory. Okay. So this is a ball with top spin actually. Yeah, so for instance, this could be tennis balls and stuff like that. Okay. All right. Now we'll look at uniform circular motion. All right, so we'll look at uniform circular motion. What that means is your trajectory is a circle and your speed is not changing, but your velocity is changing. And so we saw that when only the direction of the velocity vector changes, the acceleration is perpendicular to your trajectory. Okay? And in this case, the acceleration will point toward the center of the circle. And so that's why it's called centripetal acceleration as well. And the magnitude of this acceleration is your speed square divided by the radius of the circle. Okay? So the smaller the radii of the circle, the greater your acceleration and the greater the force that is needed to go in that circle. Okay? So it's harder and harder to go in smaller circles faster and faster. All right, I will briefly go through this proof. I don't do this too many times. So here you're going in a circular road at constant velocity, I mean at constant speed. So here's your velocity. So let's look at this instant. Okay, there's the x-axis, y-axis, there's the angle theta. So there's the velocity, and what we'll do is we'll write the velocity in its component forms. Okay. So there's the x component of the velocity. This x component is equal to, see, v, that's the hypotenuse, sine theta. There's the x component. V sine theta, okay, and it's negative. Sine theta is yp, the location of the particle, divided by r. So sine theta is yp divided by r. And the negative sign, because that is a negative, it's pointing in the negative direction. Here's the y component of the velocity. Y component of the velocity is v cosine theta. V cosine theta, and cosine theta is xp divided by r. V xp divided by r. Okay. So there's the velocity written in terms of components. And now if you want the acceleration, you just take the derivative of v with respect to time. Okay. The magnitude is constant. Okay. R is constant. So the only thing that's changing with time is yp, this location as the object goes around in a circle. This coordinate is changing and that coordinate is changing. Okay. So dv by dt is vy and vx. Okay. dy by dt is Vy, dx by dt is Vx. Okay? And then again, we write Vx and Vy. Vx, Vx is Vx is V sine theta. No, Vy is V cosine theta. V cosine theta. Vx is V sine theta. Okay, it's negative V sine theta, and we have those. And the magnitude of the acceleration is, here's the x component of the acceleration, here's the y component of the acceleration. You take, and what you get is a cosine square plus sine squared term, okay, and v squared by r. Okay. So the magnitude of the acceleration is square root of v squared by r cosine theta square plus okay, v square by r comes out, and what your cosine square theta plus sine square theta. Okay, so the magnitude of the acceleration is that. So what we have shown is when you're going around in a circle at constant speed, the acceleration is, the magnitude of the acceleration is that. Okay, and to get the direction, we want to prove that it's pointing toward the center. You see the acceleration at this point, it has a negative x component and a negative y component. So the acceleration is in the third quadrant. Okay. So for an acute angle, the acceleration is in a third quadrant. And if you calculate tan phi, a is ay over ax, which is this guy divided by this guy divided by that guy, and that's equal to tan theta. But tan theta is equal to tan theta plus 180 degrees. Okay, so this is equal to phi. Okay, so this angle, tan of this angle is equal to tan of this angle. Okay. All right. Anyway, so what I want you to remember is when you're going in a circle at constant speed, this is uniform circular motion. Your acceleration is due to just change in direction of the velocity, and it points towards the center. The magnitude of that acceleration is v squared by r. Okay. So here's a curved trajectory. Okay. When you have tangential acceleration, what does that mean? When you have tangential acceleration, what does that mean?
Speed, so you didn't change the direction.
Very good. No, speed, this acceleration is due to the change in magnitude. This acceleration is due to the change in direction. Okay? So whenever you're in a straightaway, this acceleration will go to zero. Okay? Because when you're in a straightaway, your direction is not changing. Only your magnitude can change. Okay? So on a straightaway, you can only have tangential acceleration. Okay? On a curved path, you can make the tangential acceleration zero by keeping constant speed. Okay? All right. All right, now we'll sort of, this is what this is related to. Okay, so here's a very interesting fact. Okay, so let's say you do all kinds of physics experiments in this lab, in this room, okay? And you come up with laws. And physics laws are, for instance, expressed in equations. Okay, so what you discover is the force acting on an object is mass times d square r by dt square. All right, so what we'll do is now we'll do the same experiment. We'll do all kinds of experiments, except that this room is moving at constant velocity. Okay? And we do experiments. And what we find is the laws of physics are exactly the same. Okay, in that moving frame, it might be dr squared, but the laws of physics are the exact same thing. Okay? So those are called inertial frames of references. Okay? So when frames of references are moving at constant velocity relative to each other, those are inertial frames of references, and the laws of physics are the same. Now, for instance, if you do an experiment in a spinning room, that is not an inertial frame of reference. You will in a spinning frame, okay, there will be extra fictitious forces. You will see forces that don't exist. Okay? So in inertial frames of references, laws are the same. Okay? Right, so that's our ultimate goal, but I mean, we won't go there, but so we'll build up the technology for that. Okay. So what we're going to do is, so here's an observer, and let's say here are two observers. This person is standing on the ground. Here's a lab that is moving at constant velocity with respect to this observer. Okay. So here's what this means. So let's say the person inside, so this dog, let's say, is tossing a ball, is juggling a ball. Okay. And the dog juggles a ball. And what is the trajectory of the ball inside the car? It will be a parabola. Okay? So this dog will throw a ball, and the trajectory is a parabola. This person will also see a parabola, except that this person will see the same parabola is wider. That's all. Okay? But both the trajectories will be parabolic. All right. So again, we are not going to get to our destination. We just want to build a technology. Okay, so here's one frame of reference. Okay, and here's another frame of reference. Okay, so in this example, this frame of reference would be that which is moving at constant velocity, and so on. Okay, there's the position of an object. There's an object, and with reference to this frame of reference, there's the position of this object. With reference to this frame of reference, there's the position of the object. Okay. And the location of this frame of reference is that vector. Okay. So we have, so again, there is the particle. Okay. So RPA is equal to RPB plus RBA, frame B with reference to A. Okay, so here's how you remember this. The position of particle with reference to A is equal to position of particle with reference to B, frame B, and position of frame B with reference to frame A. Okay, so the way you do this is position of particle P with reference to frame A. You can insert any symbol. So let's say you can insert another frame. Position of particle with reference to B plus position of frame B with reference to A. Okay. So that's how you remember this. You can insert a letter in between. Okay. And now you can just do calculus. Okay. So if you want the velocity of the particle with reference to frame A, you just take the derivative of that. That gives you the velocity of the particle with reference to frame A. That's equal to velocity of particle with reference to frame B, velocity of particle with reference to frame B. And what is this? Velocity of frame B with reference to frame A. Okay. So for instance, that would be the car traveling at 60 miles an hour with respect to the ground. Okay? And then you want the acceleration, you take the acceleration you take the time derivative of that. Here's the acceleration of particle with reference to frame A, acceleration of particle with reference to B, and since frame B was moving at constant velocity, this is 0. So you see the acceleration is the same in both the frames. Okay? And the trajectory would be parabolic in both the frames. Okay. All right, so this is the sort of simple example we'll be interested in. Okay. So again, velocity, so here's velocity of a particle in frame A is equal to velocity of particle in frame B plus velocity of frame B with respect to frame A. Okay. All right, so for instance, in this picture, this is, okay, so here's rain. So what we're interested in is the following, in analyzing the following. So here's rain falling straight down, and you're driving on the road. And what you want to see is how does it appear to you? How does the rain fall for you driving in the car? Okay, what does it appear to you? Okay, so let's do this. So velocity of rain with respect to the ground is equal to velocity of rain with respect to the car plus velocity of car with respect to ground. Okay, so this is what you're interested in. Velocity of rain with respect to the car is equal to velocity of rain with respect to ground minus velocity of car with respect to ground. So there's the velocity of car with respect to the ground. So negative of that would be in this direction. Okay. And so here's velocity of rain with respect to the ground. And here is negative of velocity of car with respect to ground. So this would be velocity of the rain with respect to the car. Okay. So if rain is falling straight down and you're driving in that direction, the rain will be coming at you like that. Okay. Yeah. So if you're going at infinite velocity, the rain will be coming at you horizontally. Okay. All right. So that's what this was. All right. So that finishes this.